Poiseuille's equation. Poiseuille's equation. He derived a relation for measuring the coefficient of viscosity of liquids. He derived a relation for measuring the coefficient of viscosity, for determining the coefficient of viscosity of liquids. Here I am going to explain the relation. Eta is equal to pi p r to the power of 4 by 8 LV. Pi p r to the power of 4 by 8 LV. Here P is pressure difference, R is radius of a capillary tube, L is its length, V is volume flow rate of the liquid. Volume flow rate of the liquid. To understand these parameters, see the figure. In the figure, you notice a cylindrical vessel which has a small opening at the bottom and a capillary tube is fitted in this opening. A capillary tube is fitted in this opening and some liquid is taken into this cylindrical vessel. Now, a pressure difference exists between the ends of the capillary tube inserted in the hole at the bottom. Inside the liquid, the pressure is more, and outside the liquid in air, the pressure is less. The length of this capillary tube is indicated with L. The length of this capillary tube is indicated with L, and its radius is R. Now, the pressure difference can be understood like this. The pressure outside is atmospheric pressure. Outside the capillary tube, the pressure is atmospheric pressure. So, in the end, which is in air, the pressure is atmospheric pressure. But when we come to the capillary tube inside the liquid, here the pressure exists, the pressure is more because on the surface of the liquid there is atmospheric pressure. Atmospheric pressure acts over the surface of the liquid, and the column of the liquid above the axis of the capillary tube, it also applies pressure. So, the pressure across the cross section of the capillary tube is the sum of these two pressures. One is due to atmospheric pressure, the other one is due to the water column. Hence, the total pressure is sum of these two pressures. The difference of these two pressures will be equal to HdG, where H is the height of the liquid column above the axis of the capillary tube. D is density of the liquid, G is acceleration due to gravity. D is density of the liquid, G is acceleration due to gravity, and H is the height of the liquid above the axis of the capillary tube. And this height changes as we collect some liquid. We arrange a laminar flow, a steady flow in the capillary tube. We adjust the height of the liquid such that the flow of the liquid is steady flow or laminar flow. Then we collect the liquid for a known time. And the volume of the liquid, the flow of the liquid in 1 second, is indicated with V. So, the flow of the liquid in 1 second is calculated, that is V, volume flow rate. And as we collect water, the height of the liquid column decreases. As we collect the liquid, the height of the liquid column decreases. So, H is taken as the average of the initial and final heights. Initially, if the height is H1, after collecting the liquid, the height is H2, then H is average height, which is H1 plus H2 by 2. So, the difference in pressure P becomes equal to H1 plus H2 by 2 into D into G. Like this, we understand these parameters in the equation. By using this relation for eta, we can determine its value in the laboratory. We can determine the value of eta in the laboratory using Poiseuille's equation. While doing the experiment, we should know the assumptions made by Poiseuille. He assumed that the fluid in contact with the wall of the capillary tube is at rest. And the pressure is same throughout the liquid. and the flow of liquid is considered as laminar flow or steady flow. Like this, he assumed some parameters and then derived this relation. So while conducting this experiment, we should maintain that the flow is laminar flow and the pressure is same throughout the capillary tube. Terminal velocity. A spherical body while traveling in a fluid attains constant velocity. Traveling in a fluid under gravity attains a constant velocity after some time. This constant velocity attained by the spherical body in a fluid is called terminal velocity. Suppose if we imagine that the water drops are falling through the air, after entering, while coming down, the water raindrops will be influenced by gravity and their velocity will be continuously increasing. But after entering the atmospheric air, the speed of raindrops decreases, and after some time this decrease continues until the force of gravity is equal to the viscous force. The force of gravity is equal to viscous force, and the velocity attained at this stage remains constant, and the water drops fall with constant velocity. So when a spherical body is moving with terminal velocity in a fluid, then the gravitational force, a downward force, is equal to the viscous force, upward force, or the downward force is equal to sum of the downward forces is equal to sum of the upward forces. So the resultant force will be zero on this body when it travels with terminal velocity. An empirical formula is given by Stokes to determine the viscous force. The relation is viscous force is equal to 6 pi eta RV, where eta is coefficient of viscosity, R is the radius of the spherical body, which is traveling with terminal velocity, and V represents the terminal velocity. So when a body is traveling with terminal velocity in a fluid, when a spherical body is moving with constant velocity, terminal velocity in a fluid, then the viscous force F is equal to 6 pi eta RV. The viscous force is given by the relation 6 pi eta RV. Let us derive a relation for the terminal velocity. Suppose a spherical body of radius r is descending with terminal velocity under gravity. Suppose its weight is W. Then two forces act in the upward direction. One is viscous force, the other one is buoyancy force. When it is traveling with terminal velocity, the resultant force, net force acting on this spherical body is 0. Hence, weight W will be equal to sum of the viscous force and the buoyancy force. If W is weight, Fb is buoyancy force, and Fv is viscous force. Fb is buoyancy force, then W is equal to Fv plus Fb. Using this relation, we can derive a relation for terminal velocity. If the density of the material of the spherical body is rho, and the density of the fluid in which it is traveling is rho 0, the density of the fluid is rho 0, then the weight of the spherical body is given by 4 by 3 pi r cube rho g, where r is the radius of the spherical body. 4 by 3 pi r cube rho g. And the buoyancy force is 4 by 3 pi r cube rho g. 4 by 3 pi r cube rho g. And the viscous force is 6 pi eta rv. 6 pi eta rv. We have derived the relation W is equal to Fv plus Fb. Substituting the values of W, Fv, Fb, we will get 4 by 3 pi r cube rho g is equal to 4 by 3 pi r cube rho g is equal to 6 pi eta rv plus 4 by 3 pi r cube rho g. 4 by 3 pi r cube rho g. From this relation, we can obtain a relation for v, terminal velocity, which is equal to v is equal to 2 by 9 into r square g into rho minus rho 0, r square g into rho minus rho 0 divided by eta. This is the relation which can be used for determining the terminal velocity of the spherical body.